I am so happy today that Haris has joined me to pursue a particular idea that I have about um, time and entropy and art and how these things all fit together. And Haris has thankfully done some research on some thinkers that I pointed him towards. One of them is Julian Barbour, who has a theory that relates to time and entropy. And one of the things that Barbour says that I find quite interesting is that um, he does not believe that the universe is heading towards maximum entropy and going towards a heat death, but he believes that rather the universe is moving into an ever more richly structured variety. And he likes to use this word, the variety, to explain his whole theory. And this is very interesting to me because if you break down everything that there is to think about in terms of painting a painting, there are many, many, many principles and ideas and rules and laws and all of that. But if you break it down to the very basic, it's unity with variety. So the painting has to be unified, but there also has to be variety. And so the other thing that Barbour says is that entropy as a measure, the way that it's determined in the scientific community, is always inside a box. There has to be some sort of a boundary condition in order for the calculations regarding entropy to function. But he says, what if the universe isn't a box? What if the universe is open and not a closed system? Another thing that he says is that variety is scale invariant. And the reason that that matters is that one of the things I started talking about years ago when I first had a conversation with Paul Vanderklay is that based on my understanding of art, and if the universe is a work of art the way that I think it is, then underneath all the particles, there are principles. And those principles, maybe govern is the wrong word, but it's the only word I can think of. Those principles govern the way things come together. So I want to start with a little video clip of Julian Barbour talking about ratios, because I think that that's exactly what he's getting at when he talks about ratios. So let's see here if I can bring this up, and hopefully we don't get any copyright strikes on these things. So here's Julian Barbour talking to Kurt Jaimungal, and Kurt is asking him, what is your minimum requirement for your theory?
What is fundamental in your theory?
I cannot do my theory without assuming, I think they could just even be mathematical points. You didn't call them particles. They're points because they have zero size, but there are non-vanishing distances between them. But the ones, it's not the distances. The distances are, so to speak, there to enable you then to form ratios of distances. The things that are really real, ontological, are the ratios of the distances between points. That's my absolute minimum that I can do. And I'm certain I can already build an extraordinarily interesting universe with just that and nothing else. But to really get all the effects of the different types of forces, I will need something, a more generalized form of the variety, that one that is so simple there. That's the simplest one you can possibly, but it's extraordinary how much already comes out of that. It's just, people just don't know about it.
What about?
Maybe I'll stop right there for a second, because he talks about the ratios between the particles and the ratio of the distances between particles. And when I think about this whole system of principles, let's say you have there's certain elements that make up the universe, line and size and shape and direction. Let's take, for example, direction. Mm-hmm. When you start looking at physics, and direction comes into it through vectors and spin up and spin down and all of these things about direction. But what really would matter in the universe coming together is the ratios of those different directions, the distance between those different directions and those ratios. And likewise, if you're thinking about size, you could think about large and small, but there's some ratio between large and small that everything is. It's not just large or just small. It's somewhere in between there. It's a ratio. And the reason I think that's important is that Ian McGilchrist is always talking about the coincidence of opposites. That when you look at paradoxes, you can think about the coincidence of opposites, meaning that the opposites come together at some point and become the same thing, become a paradox. But that doesn't really provide for variety. In order for there to be variety, there has to be a ratio between the opposites. So that's one of the things I'm thinking about just to begin with. And I don't know if you want to comment on this right away, or should I play the Nathan Jacobs clip first?
What I wanted to add quickly is that everything that you said is really intriguing and especially interesting to me. Both generally speaking, but also because I am deeply interested in your theory, but also in my theory, and I can sense that Julian Barbour's work resonates with both of our theories and ideas, and I find that fascinating. What you mentioned about his insistence in terms of ratios, I picked up in another interview that he gave. I think it was a smaller channel. Let me see if I can quickly find it. Yeah, it was a channel. The podcaster was Arjun Kemani. And in that specific interview, and Julian Barbour mentioned that nothing without ratios. And he then added that I'm joking here, but I have already expressed this idea to my children to have this adage engraved into my tombstone. So, yeah.
Yeah, I heard him say that too about his tombstone, nothing without ratios.
Yeah.
And I mean, if you once understand how these principles, let me just go over the principles again for those who, this isn't all the principles, but this is an example of principles. Unity, harmony, contrast, repetition, variation, gradation, balance, and dominance. Even if you think about balance, there has to be a ratio. Even when something seems perfectly balanced, it's still a ratio of some sort. But usually for creativity to take place, there has to be some little imperfection in the balance, right? Mm-hmm. So in order for energy to arise out of something, it has to be at disequilibrium. So everything is a ratio. And when you're painting a work, there are always ratios, even if you're just drawing a straight line, just because of the way the hand works, there's going to be a certain amount of gradation in the width of the line. There's going to be a certain amount of gradation in the pressure. that's exerted on the line that makes dark or light happen in it. If you're making the line out of a particular color, there's always going to be a ratio of how warm or cool that color becomes as the paint dries even, or I mean, it doesn't matter how much you try to make something perfectly something, there's always going to be a ratio involved. So I totally understand what Barbour is saying when he says nothing without ratios. And he says from that, you get an extraordinarily complex universe. Mm-hmm. So do you think this would be a good time to play the Nathan Jacobs clip?
Yes.
Okay,
yes.
So let's put that one up here. And I'm going to have to move something out of the way to get here. Okay, so Nathan Jacobs is talking in this one about the purpose of creation and why there is so much variety in the world.
Are rather diverse, and that diversity of those things, in order to truly articulate it for any sort of observer, you really do need an entire portfolio. And so in the same way, if you wanted to understand, the work of Bach, for example, the genius of Bach, what you'd have to do is you would have to look at all of the different things he's composed over the course of his life. And only then do you start to get a fully three-dimensional view of his creative powers. And so it is with regard to God. If the divine nature just made angels, that would certainly tell you something about God, but it wouldn't tell you everything about his creative power and his wisdom. And so what you see is that the entire concept of the great chain of being is that this hierarchy of beings, from very humble beings like rocks and plants to more sort of impressive and dynamic beings like animals and rational animals and angels, are all meant to fully flesh out and articulate the divine wisdom and power and goodness and justice and all the like. And then also with that, what you start to find is, again, like I've used the analogy with regard to art, the idea that different techniques are incompatible. I've used this analogy in past episodes where I talked about like certain painterly techniques. The entire point actually is to see the movement of the paint. And so it's thick paint and it's quick and it's painted wet on wet and things like that. And then there's these other very long form, sort of like glaze painting, for example, classical forms of painting, where you don't want brush strokes. And part of the refinement and the layering and the drying is all part of the process. And those are incompatible. But they are both expressions of artistic prowess. They are both expressions of the artistic powers or skills that are within the artist. And so in the same way, when you're talking about God, to only make one type of being, for example, is to actually only offer you a small glimpse of articulation of the divine nature. So the diversity of the chain of being is there specifically in order to fully flesh out and articulate, filling up the concept of God, which with as much content as possible, so to speak, all the different dynamics of divine wisdom and power and goodness. Now, with this, what you also find is the conviction that our world is actually one creature in some way. This is a sort of thing that actually emerges. It emerges in Plato's Timaeus, where it becomes apparent that the forms are not just a series of, sort of archetypes, archetypal statues that sit in some, transcendent museum or something like that, but rather there's a recognition that when it comes to creatures, there are overlapping properties. The forms overlap. And this was
I'm going to break here. I think if they get too long, that's when you get a copyright strike. And I'm just going to scroll up to this spot here. And
go through a truth table, for example, and you can start to identify all the different ways in which things might combine. So when you start to articulate or finitize something, what you start to see is that the intersecting possibilities, right, the overlaps and the disconnects are the very things that create that type of diversity, right? What
the intersecting overlaps and all these intersections are what create the complexities. And so maybe that's enough of watching other people's videos right now, and let's hear what you have to say now, Haris, about all this.
Yeah. First of all, as I said before, I find this whole thread, like we have two seemingly distinct fields of inquiry here. We have a new theory of physics proposed by this great historian of science and of physics, that is Julian Barbour. And he's proposing this notion of the Janus point, that the universe started with it started with the Big Bang, as many of us and many scientists call it, but that initial point in his own cosmo-conception is what he calls the Janus point. So it was the lowest possible point, and out of there, the universe started to grow. And I have a figure that I tried to paint myself on Microsoft Paint. I will share at a later point just to clarify that idea from Julian Barbour. But we also have, on the other hand, Nathan Jacobs here making this theological argument, and I find the common thread to be fascinating. Both of them, at least to me, they share these common elements of Platonic thinking, that in one way or the other, it got into the Christian mindset as well. You have this realm of the idea, and when you try to find something that you can actually measure in the real world, it will not be exactly this idealized version of either of the Platonic solids or of the ideal ratios. And we have many different ratios that they are very important, and they are found everywhere in nature. We have this, the golden ratio, for example, phi. And of course, this is an irrational number. So you cannot, we can grasp it by having this symbol of the phi letter. But it's like, it is exactly the same case as with the pi, that it is describes the circumference of the circle. We have these abstractions, but we will never be able to fully grasp the vast, infinity behind those idealized notions. But our approximations are good enough in order to ponder and to think about it, and even to innovate and have useful and many times thought-provoking conversations like the one we're having now. So
another interesting ratio is Euler's number, right?
mm-hmm.
Yeah. And what's really interesting to me is how anybody ever figured out any of those numbers and ratios. What was it that led them to that? Like the golden ratio started out with some guy thinking about rabbits cohabitating. So I mean,
Yeah.
it's so interesting the way the human mind works. And I guess that I was thinking about AI the other day. This is just a side point. This has nothing to do with anything, but I was thinking, what if AI existed? Let's say AI existed back there when Fibonacci was thinking about rabbits, before he started thinking about rabbits. And let's say that AI had a database of all the information and knowledge and wisdom that existed in the world at that point, before Fibonacci had his idea about the rabbits. If you had asked AI at that point, think about rabbits. What do you get from rabbits? Would AI have come up with the golden ratio? I just think if we took all the knowledge of the world before Einstein and then asked AI, to think about Newton's gravity, would AI have come up with general relativity?
Yeah, to Being completely honest, I am still not convinced that AI can make significant breakthroughs. Some people, they are pushing back on that from, especially in terms of soft sciences. Like, because AI, at the end of the day, it's very good at picking up patterns, and we human beings, we really appreciate that, especially if we have like an artificial tool like AI showcasing to us like, hey, there is this hidden pattern over there, have a look. That's good. That has to do with a decision support system in a way that facilitates the scientific process and the discovery of new theories and hypotheses. But as far as I am concerned, with my experiments so far with LLMs, I am not convinced that, at least at their current form, LLMs are good enough with math. Like, maybe they are very good at tackling these complex hidden relationships within literature and trying to find the common thread between different ideas, but they fail spectacularly in the simplest mathematical tasks. So even if you ask an LLM like, is this number a prime number? In most probability, if you give if you input like a large enough, they will probably and do not find the correct answer to it. So
Wow.
and the reason is because they due to their architecture of this transformer, they got trained in order to make the best optimal prediction concerning the next token, right? So their training set was the vast literature that exists out there. So they got trained in terms of literacy, but not in terms of numeracy. So yeah, hopefully
so that brings me back.
Someone like Wolfram
Uh-huh.
would be able to push the envelope forward with all of that.
Yeah. Well, that brings us to prime numbers. So your theory about primality, do you see anything in that idea that you have that would connect up with ratios, with Julian Barbour's idea of ratios?
Oh yeah, and definitely.
Is there any sort of a way of looking at ratios where, when you're calculating where the next prime is going to be, when you get up into really big numbers and you're trying to figure out where the next prime is going to be, could that in any way be connected to ratios? Like,
okay, I will give you one example. It doesn't have to do with prime numbers, but in a way, prime numbers pop up, have this tendency to pop up everywhere. So we were discussing before about, you mentioned the Fibonacci sequence, right? And the Fibonacci sequence is heavily linked with the Pythagorean triplets and the Pythagorean theorem. So, for example, the Fibonacci numbers, you start with 0, then you have 1, and you keep adding the two previous terms, right? So we're going to have 1, 2, 3, 5, 8, 13, 21, and so on. And the famous Pythagorean theorem states that a squared plus b squared equals c squared. And we are going back to the triangles once again. But there is a connection that I am not sure that any LLM was going to be able to spot that one out. But for example, if you take, instead of the alpha term within the Pythagorean theorem, and you inserted like something akin to if you take if you take the product of the next Fibonacci number and you multiply it by the number after that, and you double it, and then you square it, and you assign that number to the number, how you call it, to the symbol A. Let me just quickly share something just to help people understand what I'm saying here.
Yeah, I think it would be helpful to be able to see that.
Yeah.
Because whenever I hear mathematics, it always sounds like magic.
Yeah. So I don't know if you can see my screen here.
Yes,
Yeah. Okay. So this is a very, very simple formula that behind it has exactly this a squared plus b squared equals c squared. So this number is the Fibonacci number that, for example, this is n plus 1. So that will be the second term in the series. If you, I don't know, if you assign the number 1 to n. So if you take 2 times that number and multiply it by the next number in that sequence, you square it. So you in a way you are emulating the a squared plus b squared, and you apply the same logic for the b term here. You can see that you can literally predict this this term that is way far ahead in the Fibonacci sequence. And this term, if our n, for example, is the number 1, then it's gonna be like the fifth Fibonacci number. And we can do this with actual numbers. If you want to just quickly give an example to everyone listening.
yes, I would like to see that.
Yeah. Okay. So, yeah, let me quickly.
So we're talking about numbers within the Fibonacci sequence.
Mhm.
Can you start anywhere in the sequence or only starting
Yeah.
at the very beginning?
No, you can start anywhere.
Okay.
So let me stop sharing and I will bring. Yeah. Right. Will bring my old friend, the calculator. Okay, so we have, so the Fibonacci number is like, we start from 0, we go, the second term is 1, we have 1 again, 2, 3, 5, 8, 13, 21, right? 9. So that formula said the following thing. Let's take, and give me a number for n, just a small one, just to start.
Let's say 2.
2. Okay, so the formula said to take the n plus 1 term. So that will be the third Fibonacci number term in that sequence. In this case, it's 1 because we start from 0, we go to 1, we add up that, and we arrive at 1 again. You multiply that by the next one. The next one is 2. You square that. And then the b term, the second term, says that take the nth term. So that means take the second term, multiplied it by the fourth one. So that's 3. Square that. You have 25. And according to our formula, if we take you said n is 2, so that means 2 times 2 plus 3, that's 7. We have this term over here. When we square it, we can see that it's the correct prediction. So we can keep doing that for any other term too. So that's an interesting little bit of a connection that is going on in terms of Fibonacci numbers and these Pythagorean triplets.
Well, but where did that formula come from?
Induction. So a lot of people, they started working on trying to understand such sequences, and especially the Fibonacci sequence, as you mentioned, is a very interesting one that can be found almost everywhere in nature, but also it is deeply embedded into our digital version of the world. Like we can find it in terms of fractals. We have the Mandelbrot set. There is something that it is called like the 3D version of the Mandelbrot set. And you have these numbers that they keep repeating. And it's a very simple rule. So we're going back to this idea that you don't need to have very complex rules. You just have something very simple, like add the two terms together and keep doing that in order to find the next. But when you analyze, because of this initial simple rule, you can analyze that sequence, and there are a lot of tricks where you can extrapolate these hidden connections and arrive to different formulations in order to go forward and actually figure out like a very specific term without having to go through the exact process of adding the previous two terms together again and again. So
in this case, they analyzed it using the Pythagorean theorem, a squared plus b squared equals c squared. Are there other sequences of numbers that are analyzed using the Pythagorean theorem?
Well, I think there is some work done in terms of the second. There is another ratio that is very, very close to the Galton ratio, and it is called the plastic ratio. It is usually denoted by the Greek letter rho. And that one, it arrived from a Dutch theologian and architect, where he was trying to come up with a ratio that will be very aesthetically pleasing, much akin to the Galton ratio. So he came up with this new ratio that he called plastic. I think the reason he called it plastic is because you can also find it applied into the plastic arts. So not only architecture, because the fine arts, there are 5, if I am not mistaken. You have painting, you have music, you have architecture, you have sculpture, and also poetry. I'm not sure if poetry counts in this one. But it is a very, very, very nice idea that you can have a ratio that can capture this abstract sense of the aesthetic. So, yeah. So I will have.
So what do you think is the implication that triangles can be used to analyze like the golden ratio?
Yeah. Well, it seems to me that if there was like it is what Barbour is saying, like if there is like a minimal shape that is eternal, that you can always be certain that it will be there, it's the triangle. And you can also see that in terms of digital physics, like with the algorithms, and in terms of rendering and animation and all of that. Everything works with in terms of triangles. So you can triangulate almost everything. It's the most commonly found shape in nature. And even the five Platonic solids, or all of the other solids that they arise out of them, if you think about it, they are comprised out of triangles.
Mhm.
Like, even if we are talking about a tetrahedron or an octahedron, still we have these triangular surfaces. So, yeah.
Well, even Wolfram's theory, whenever he illustrates the hypergraphs, there are always some form of triangle that's arising out of some other form of triangle.
Yeah.
And it always has to do, and the difference in the kind of universe that's created is based on the variety of distances in between the nodes and edges. But those nodes and edges are always forming triangles.
Yeah.
So yeah. So, well, what do you make of all that? Barbour says that Barbour has an idea about time. The common idea about time is that it's the motion of moving towards maximum entropy that actually determines the arrow of time. But Barbour says no, because we're not moving towards maximum entropy. We're moving towards maximum richly structured variety and beauty. I rather like that. So that would change the whole theory of time. So did you give any thought to that whole issue of time when you were doing the research on this?
Oh, yeah, because one of the things that arised out of my own theory is that both time and space are emergent. So I was really happy to
Both time and space are what?
emergent properties. They are not fundamental properties of
okay. Emergent. Okay.
emergent. Yeah. So first of all, allow me to share here. This is apologies for the lousy illustration, but I wanted to have this diagram in order to share it with everyone. So this comes from Julian Barbour's idea of what he is calling the Janus point. And Janus was a Roman god of thresholds, and he's depicted as a two-face, so looking in both different directions, left and right, or I don't know, front and back. So his idea is that the Janus point is what everyone is calling the Big Bang. So the first thing that stands out is that he doesn't disqualify the notion of the Big Bang. Okay. Now, what he's saying is that the Big Bang was the initial point, that it was the most coherent point, to say it like that. It was like a minimal point, and everything, as you said before, it grows and grows in terms of being in terms of their variety. So his vision, it's an optimistic one. The universe is not moving towards decay, but it's always moving into higher and higher notions of order. So as Julian Barbour mentioned, if we take it that this minimal point, it's what he calls the Janus point, if we accept that, then after the Big Bang, we have this shape arising. And the arrows that going in different directions, you can imagine that our universe is only half of it. So in his cosmoconception, we are only able to see only this part. And this is why we get this illusion of the time arrow flowing always forward. So, yeah. And at each different point, this illusion is persistent because as with the case of ratios, even if you change the numbers there, the ratio will still remain the same, right? So this is why this illusion that we experience as time progressing is so persistent. Yeah.
So one of the things that I thought about when I was listening to Barbour, because he makes me think a lot about this whole issue of art, is one of my teachers said, in art, you're not painting things. Always keep in mind, you're not painting things, you're painting relationships. So it took me a long time to grok what that actually meant. At first, I was thinking maybe the objects are related to each other in the picture frame. But that's not really what he meant when he said we paint relationships. What he meant was you're not just painting the relationships of the objects in the frame, but every stroke of paint that you're using is a relationship with the previous strokes of paint that have been laid down. So every new stroke of paint is facing a new context because the context that the previous stroke of paint laid down is now a context that was different than the stroke before that. So every single stroke of paint creates a new context, and the next stroke has to relate to that context. And the way that it relates to that context is in these different intersecting ratios of these principles. Is it lighter or darker? Is it more intense or less intense? Is it creating gradation or not creating gradation? Is it making the object smaller or larger? And all of these things are intersecting at the same time. So it's not just one choice, but it's all the choices that are happening with every single stroke that gets laid down. And so that would be true, even if you're just talking about point particles at the beginning of the universe. And so I don't know if you remember seeing that illustration that Barbour put up. I don't know if I could find it very quickly, but he had these little circles showing all the different points and the way that the variety would grow of the distances between points from one point in time to another point in time. And it's continually becoming more and more variety and more structure within this set of points, which is very similar to several things that I think about. One of them is has to do with boundaries. Whenever boundaries are set, when the boundaries become more constrictive, there actually becomes more structure inside the boundary. And that was the work that was done by Sharon Glotzer with the particle physics, where she began removing space from these particles, and the particles would automatically form up into a crystalline structure. They wouldn't just stack up all next to each other. They would actually form a very complex structure. But also, okay, I forgot the second one. It'll come to me. But this whole idea of time and the way these things intersect. Anyway, I don't know if that sprang anything for you when you're thinking about it.
Yes, and I found a clip that I would like to share. with you. It has to do with what my good friend Chance Mills calls he had this idea of implicit lines of inversion. And
Implicit lines of what?
Implicit lines of inversion.
Inversion.
Yeah. And in a very peculiar turn of events, I shared something with him that I found fascinating, and it actually captures that abstract idea that he had, but in terms of art. So there is a Cuban artist called Carmen Herrera. So
this is kind of this amazing moment. She's still in Paris in 1952, and I think this is kind of the moment where those elements that become part of her signature style really come into play. So she did a series of black and white works in 1952, and I think you see here that she's now distilled it to two colors. That she's actually, again, not using contour lines, that diagonal stripe that you see run through the painting. It's just a color shift. She's not actually making a line. It's just that the diagonal bars of color end and then flip to their inverse. She's also painting the frame. So I don't know if you can see this, but at the bottom and top of each bar, each color, there's just a tiny strip of the opposite color. That's the frame. So she's starting to incorporate the physical support, those elements into the work. So this is kind of this.
Yeah, I found that painting fascinating because she's not using any like lines. She just the inversion. So yeah.
Now that was one of the most interesting things that I learned about when I started studying painting from an angle more of creativity and not just, let's say, artistic skill or something like that, is that edges are so important in a painting. And you think that that you would put a line between one thing and another, but you don't have to actually put a line. You just paint the thing, and that the edge of that thing creates the line between it and its counterpart. But when you're painting the thing, then you have to think about that edge between the two in a way that doesn't distract from the rest of the work. So maybe that edge is not the most important thing in the painting. So then you want that edge to be slightly fuzzy so that it's not so obvious. But there's another part of that edge which would directionally lead you towards the focal point. Then you want that edge to be sharp so that it catches the eye and leads towards the focal point. So edges become very, very important on whether they're fuzzy or permeable, whether color and value can move back and forth between the two objects through that edge, or whether the edge is a very sharp boundary. So like you notice when you're looking at posters, a poster generally has very sharp lines around everything, or animations, usually very sharp lines around everything, which removes a lot of the subtlety. So subtlety and variety come from carefully working the edges so that they move the eye around the painting in a pleasing way.
Yeah. So I think if I am allowed to do this, to draw this speculation, I think this notion from Barbour about time being emergent and an illusion, we can understand it in terms of similar illusions, visual illusions, like this diagonal line is not there, but it arises out of this constructing of the different elements that they are coming together. So maybe this is the same.
So this is what you're getting at is the whole emergent aspect of time.
Yes. Yes.
that
Yeah.
the edges aren't here, but the line isn't there, but it emerges out of the
Mhm.
just the inversions that are happening. Oh, that's so interesting.
Yay. I was glad that I was
Yeah.
able.
Okay. So wow, that's interesting.
Awesome. Awesome. Okay.
So time is arising out of the inversion of the Janus point,
Hmm.
is what he is saying.
Yeah. Yeah. Yeah.
Because time is a line. I mean, we think of time as a line, right? We're always talking about the timeline. Now, in Wolfram's theory, time is the only way that time exists is that it is the updater of events. Every time one triangle changes into another triangle, or the distances between triangles change, every time that happens, that is an instance of time. So time is actually causal in that sense, that time is causing the updating of events. But it's not like a continual flow in Wolfram's theory.
Yeah.
And in Barbour's theory, does he see time and space as discrete or continuous, or does he talk about that at all?
He talked about it, and I think he was making a very specific distinction. I'm not 100% sure how, if I remember it correctly, but yeah, let me quickly go through my notes, just in case I have it. Okay. Okay. Since everything in the universe interacts with everything else, every indifference must be taken into account to obtain the exact measure of time. The universe is its own clock. What happens locally is the outcome of everything in the universe. So that was another point that he was making. And he tied that back because, as I said in the beginning, this is a point that it became apparent to me while I was studying his different articles. Julian Barbour is an amazing historian of science, and this is something that also Carlo Rovelli pointed out. He was able to go back and revisit the very early the first papers that came out with these fascinating ideas that everything that we now know got built upon. So instead of going to Einstein, he went back to Mach.
Mm-hmm.
Yeah, and
Yeah.
he was able to review that with a clear lens. He tried to understand, like, yeah, but why Mach says that thing here? He said that thing because Leibniz 200 years earlier said that thing. So very carefully, as if he was like an archaeologist of ideas, he started slowly and building up this notion of the Janus point. And yeah, I think it's fascinating, and it has to do with this interplay between the discrete and the continuous. So yeah.
Well, let me see if I can bring up this. I'm going to I'm going to try to bring up this other video. And I hope I have the right one. There's a point at which he starts talking about I hope it's the right video. I have so many things brought up at this point. maybe this is not it. He starts talking about his Keplerian pairs.
Mm. Yeah, yeah, yeah.
Is that in this one?
Don't know if I have.
That's not that one. So I've apparently mislaid.
I think it was
Oh no, it
in
is here. It is here. Okay. Okay. So let me just play this.
that
It's the one
universe,
with
and you could
Palindromic.
look at its shape, what its shape is, and the shape is most uniform at that Janus point, and as it goes away from it in both directions, the shape gets more structured. Clusters form, and those clusters, particularly you get Kepler pairs forming, that's two particles going around each other in Keplerian orbits, and as they do, all of these ones, they start marching in step. Each Kepler pair becomes a rod, clock, and compass all in one, and they all are marching in step, becoming synchronized with each other in a most fantastic growth of order. So at
But
the
just
Janus
so I
point,
understand,
it's where it...
But Julian, just so I understand, so you're saying these Keplerian pairs, which are just two particles orbiting around each other, in essence become a clock because it's cyclic motion, in essence become a rod because there's some specific separation between them.
That's the major, the length of the ellipse,
the major axis, and that gives you a compass as well because you've got a direction that's picked
compass
out.
as well, yeah.
Okay, so this is very interesting, this rod, clock, and compass. Now you were talking about the clock. You mentioned something about a clock just moments ago, and I lost what it was you said about the clock.
The universe, it's its own clock.
Okay, so the universe is its own clock, and he's saying that every Keplerian pair, which is basically just two pairs connected by a distance, it is a rod because there's a distance between the pairs, and then it's a clock because it's got a cyclic motion as it's rotating around, and it's a compass because of the direction. So that all has to do with ratios, but then it also made me think when he interrupted Barbour mentioned something about it's the elliptical axis. So when he's talking about those 2 points, then is he thinking of them as the foci of an ellipsis?
Yeah. This is how I also understand it. And
because there was a time, and this is probably heretical, but there was a time when I was thinking about the Trinity and thinking about the two foci of an ellipsis and the ellipsis as being a triad.
Okay.
Because some of the early church fathers talk about, or maybe not the early church fathers, maybe it's a Catholic thing that they talk about the Father and the Son being joined by the love of that the Holy Spirit is the love that joins the Father and the Son. So when I visualize that, I visualize it as two foci with being surrounded by an ellipsis.
Okay, that's very interesting. There is also something we call perichoresis. I don't know if you're familiar with that term.
How do you spell it?
Perichoresis. Let me.
Perichoresis.
Yes.
Okay.
And it is a term that it comes from the Orthodox tradition of Christianity, and it is referring to the relationship of the three persons of the triune God. So you have the God the Father, God the Son, and God the Holy Spirit, and there is this notion of the rotation and the indwelling They are both distinct, but there is this sense of the rotation, and I find that fascinating because rotation is also something that you can observe everywhere happening in nature, and there is something remarkable about it because you can also see it even in the equations and the formulas of found in quantum field theory, and whenever you have like the symbol of pi manifesting in one of those equations, one can be very certain that it has to do with this rotation element. So even if you can imagine that something like the Planck's constant, it has to do also with this pi. So the physicists, they use the so-called h bar, that is the reduced Planck constant, and basically they are taking the Planck constant and they divide it by 2 times pi or tau, as they call it. So I have this hunch that it has to do with even the Planck constant, that is the minimal length that we can observe, not that we can measure. It has to do with this rotation, and even if we extrapolate into the daily life, and we get into experiments that have to do with geometric probability, we can still think of instances where this pi and therefore the rotation keeps popping up. So there is a famous problem that has to do with geometric probabilities that comes from either the 18th or 19th century. It is called the Buffon's needle problem. And this problem it goes like this. Imagine that you have different set of stripes that you place on the floor, and you make them all equidistant between each other, okay? And each stripe has the exact same length. And then you take a needle and you throw it on the floor, and you ask the question, what is the probability that the needle will land between one of those stripes? And when you do the math, and when you look at the simplest form of that answer, the answer is like 2 over pi, which is very counterintuitive, because you will not be expecting pi to show up in such a probability game or problem. But the reason why pi appears there is because when you drop the needle rotates. So it includes this rotational aspect hidden within the actual confines of the experiment. So, yeah.
So that's very interesting thing. And going back to Planck's constant, thinking about the smallest possible distance. Distance in itself implies 2 points. For there to be a distance, there have to be 2 points, right? So it's the distance between 2 points. So that's his Keplerian pair right there.
Yeah.
Right. So to even have a Planck's constant implies that even at the very smallest, there is a distance. And of course, thing that's always interesting to me is that every distance requires a measure. And Barbour, even when he talks about these measures, he says any measurement has to take place, has to be using a measuring rod outside the universe,
Yeah.
right? And we've had a number of episodes where we talked about measurement and the measurement problem. And the reason that you need a measurement from outside the universe is that every measuring stick or device that we might use that's inside the universe necessarily has an imprecision to it. It can never be perfectly precise. So in order to have a perfectly precise measurement, it has to come from outside the universe. So I thought that was really interesting that Barbour said that.
And being fully transparent here, when I encountered that part from him mentioning the Keplerian pairs, in my mind, I said to myself, yeah, that's my twin prime pairs. Like it's, yeah, that's
Well, why wouldn't it be your twin prime pairs, right?
And the reason is because the distance is the minimum possible there. So,
well, so your twin prime pairs, is there, I come back to this thing again. If you could plot them out on a number line, is there any recognizable ratio that repeats, any pattern of ratios that repeats along the number line to finding a twin prime? Or is it just random? Could that be used as a random number generator, the distance between twin primes, or is there a potential pattern there?
The current consensus is that it seems that is quasi-random. That's the technical term. So it's not exactly random, but it appears to be random. So that's the
just because we don't have enough information.
Yeah. It appears to be random. So it's like it's not exactly pseudo randomness, something that we use when we generate random, in random number generators. Those, they are not truly random. They are based on this notion of pseudo randomness, but the prime numbers specifically, they are quasi-random. It's something very distinct. And there is a lot of ongoing research in terms of primality and specifically number theory in order to make these arguments about the, to prove the conjectures. Like, are there an infinitely number of twin prime pairs? Nobody knows. Almost everyone of the number theories, they believe that that's the case. Like, we will never reach a point where we will be unable to find another prime pair. But it makes sense that as we move away and away from the 0 point in terms of the number line, those twin prime pairs become more and more sparse. And the current research as of 2014 is that they were able to provide a proof that it is true that at least a distance of 246 it's there. Like, you will be able to find two prime numbers with that distance. And there is a lot of speculation to narrow that number down. Like, some of them, by accepting some of the strong conjectures, even the Riemann hypothesis, that basically most of maths, they are based on that Riemann hypothesis. So if that somehow appears to be false, all the mathematics that as we know it, will collapse. But if we accept that argument, then it seems that mathematicians like David, like Terence Tao and Mayer, they were able to narrow down that minimal distant number to the number 6. So that's the best they came close to do it. And even that's not like it depends on that conjecture. So we are certain about the distance of 246, and that's good enough for now, I think. Yeah.
That would be the largest distance between.
Yeah, initially the first huge progress it came from someone that was working outside of the field, and he was the one that he was able to make significant progress. And when he released his paper, he set the distance to an arbitrary large number. He said like the distance is 7 million. So it wasn't a very impressive result, but it was impressive because of the tools he used in order to arrive to that specific result. And then all the great number theories, they were able to build upon that and slowly, drive that distance down. But the idea is to drive it all the way down to 2. So very recently, I was listening to a video from Sabine Rosenfelter, and she was making she was reviewing a paper coming from China that they were able to devise a quantum algorithm called how they called it. Quantum annealing. That's the name of the algorithm. And they were able to crack the so-called RSA challenges of a 2048 bit number. And that means they were able to find the 2 factors of a semi-prime. And Sabine was saying that that's not very truthful, and I also agree with her. So I went and I reviewed that paper by myself, and I realized that they were cheating.
Oh.
And the reasons why they were cheating is because they gave these very huge prime numbers, but it seems that the distance of the numbers, if you analyze them, the distance was like either 2 or 6. So that's very small, and it has almost no value in terms of being cryptographically interesting. Like you can easily break that type of a challenge, and you don't even need a quantum computer to do it. I was able to do it with my computer. So, there is an element of, it has to do with publicity, because there is a lot of things going on in terms of selling and investing in quantum computing. And there is a lot of this upselling that is taking place. So, yeah.
Well, we have probably just a few minutes left, and I wondered if you would like to maybe talk about how your theory, talk about your theory just a little bit, and what you saw in Barbour's work that might be connected to it. Excuse me.
Yeah. Well, my theory has to do with a result and a proof that it is associated with group theory, and specifically the finite groups. And I was particularly interested into the most difficult case, that is the master group. I was able to have a nice result that has to do with the minimal order of the master group, and I was able to define it in terms of twin prime numbers. That the structure behind the master group, that it's a huge group in terms of dimensions. It can be understood as the same structure behind twin prime pairs. And I was able to make this connection. Out of that connection, some very other interesting scientific observations came out. One of them was that there seems to be an underlying structure behind that proof of mine that indicates that maybe there is some sort of a spillover effect from number theory and group theory all the way into the domain of physics. So that was my initial hypothesis. For the past 2 years, I am exploring that. And I got some very interesting results in terms of quantum information theory. Maybe we can discuss that at full length at another episode together. So it seems to me that one of the main results arising out of my work is that I am almost convinced, although I cannot fully prove it yet, that indeed time is emergent. Time is just another dimension. It is practically indistinguishable from the other three. The only reason that we are distinguishing it is because we humans, we like to operate with abstractions. That's how we understand the world and the phenomena around us. And I am taking it even a step beyond Barbour. Like I'm saying that not only time, but also space is emergent and is not fundamental. And this goes back to this notion that from my theory that at the end of the day, it's a theory about a group, a shape. I was able to associate it with one of the Platonic shapes, namely the octaedron. Therefore, my theory is volumetric. And because I'm using this novel paradigm, I was able to imagine the universe as an octaedron, that when you try to understand it in terms of a movie, that you have like different points in terms of time as we understand it. If you go forward, you will see this octaedron growing in both directions. So in a way, it's similar with Barbour's Janus point. Just doing it in I am just thinking about it not in 2 dimensions but in 3D. So it works better for me. And I was like able with this toy model of mine to play around with things with very difficult questions, but very intriguing questions like, okay, what was the Janus point? What was the point of the Big Bang? And what happened right after that? Like everybody knows what happened like from some point onward, but nobody really knows what took place and during those very, very first instances. So I was able to glimpse into that, and maybe I'm right, maybe I'm wrong. Personally, I believe I am onto a very good route there. Whatever the case, it is fascinating, and I think that it offers a very good paradigm and a novel way to grasp what was going on in our universe. And yeah.
And you're talking to people about that right now? You're having some conversations with.
Yeah, and I am also active, as I told you in before. with the Active Inference Institute.
Mhm.
So I am trying to also see how that can inform also my theory, apart from the other things we're doing there. And yeah, I am also looking in very different arenas. Like I am following Stephen Wolfram very closely. I got very recently. I got the chance to understand how his own theory evolved, because he was facing very strong critiques, and he was able to pivot in a way. So he started with what we can call like automata, like simple automata.
Mhm.
He then evolved it into hypergraphs, into graphs and hypergraphs, and now we have this full-fledged, like the Rulliad and the hyperrulliad and all of that, which is a very nice and fancy way of describing his mathematical physics. So, yeah.
Well, one of the fascinating things to me about the whole hyperrulliad thing is, and I've mentioned this before, in one of his working sessions when he's talking to one of his colleagues named James. James is talking about the hyperrulliad in this episode. It's not a video that was made for public consumption. He records all of his working sessions where he's just talking to people randomly about things. And this happened to be one of those sessions. And 90% of it is just very hard to follow. And then this thing just popped out to me where James says, it's absolutely essential that every particle, or they use the word eem instead of particle because they're talking about something very much smaller than the standard particles. Every eem has to have a unique user ID. And it meaning that every eem has unique characteristics. And if that were not so, the entire universe would collapse. Well, I was thinking about that, and I was thinking, even if every eem is identical, but the distances between the eems are each eem is in a unique context, that would give every eem a unique user ID because you could identify the context in which the eem is residing. And so again, it comes down to distance. The distance between the eems establishes the context of that eem. And so it goes back to Barbour's thing about ratios. It's the distance between particles. And so then I was thinking, well, okay, we believe that before everything, there was God. In the beginning was the Word, and the Word was God, and the Word was with God, and the Word was God. Then that means that time and space are a creation of God. God created time and space at the same time that he created the universe. Well, so then, Nathan Jacobs was talking about the reason there's so much diversity of elements and objects and things and living and non-living things is so that God has a full expression for his creativity in the universe. But then why time and space? So time is necessary so that change can take place. And if everything is about transformation, with the Janus point, the idea is that everything is moving towards perfection, moving towards beautiful, rich complexity. So moving towards God. Or Sevilla King, it's moving towards quality, right? And everything is moving upward.
Yeah.
Then change is necessary. So, but why time? Well, I mean, why space? Well, without space, there can be no distance. And distance is required for context, but distance is also required for measurement. And measurement comes down to the whole issue of judgment, basically. But it's not the kind of a judge. I mean, it's judgment in the sense of when something is true, we tend to think of that being like factually true, but true can also mean that it's lined up, that it's true to the pattern, true to the model. And that is a judgment, and that's a judgment that has to do with the distance, how far something is from lining up, right?
Yeah.
So anyway, that's all the stuff that came into my mind when I was thinking about time and space.
That's very interesting and fascinating. And yeah, in terms of your own theory, like all those principles of harmony, of we have dominance there, right?
Mhm.
So dominance, for example, is like something dominates, right? So something stands out, and it commands our attention, our focus, our it even guides our relevance realization mechanism, to use the Verwegian term there. And then you have like things like repetition. Things keep repeating, and out of that repetition, we are able to distinguish patterns, right?
Mhm.
So, and that allows us to find things like the similarities, but also the minute differences out
Mhm.
there. And when we are talking about variation, it's exactly that. Like you allow room for these differences and the similarities to coexist at the larger canvas of life and
Mhm.
the and going back to the notion of the points. Well, in mathematics, when you have a point or even a line, it doesn't really have any width, you know. So it's like that we imagine it with an actual line there that somebody draws. It's like an additional abstraction that we're making, and it's very similar to that painting that I showed you before.
Mhm.
It's not that we go there and we create the distance between the 2 points. It's that we agree that point A and point B, and we measure, and then we can see the distance. But there is no width to be found in either
Mhm.
point. No? Yeah.
Yeah, so I don't know if you ever looked at projective geometry
Mhm.
and how even a line can be seen as just the edge of a plane,
Yeah.
right? And even a point can just be seen as the intersection of a set of planes
Yeah.
intersecting in space. And that's the way I think about all these ratios.
Mhm.
That the lines and points are just intersecting planes, and each plane is made up of all of the possible, all of, let's say each plane is infinite in the same way that the distance between 0 and 1 is infinite.
Mhm.
So the space between large and small is infinite, and it
Mhm.
comprises an infinite plane. It's not just a line from large to small, but it's actually everything that's possible between large and small is on this plane, and everything that's possible between orange and blue is on this plane, and everything that's possible between thick and thin is another plane, and all of these planes are intersecting in space, creating these points, and the points are what the universe consists of. That's the picture that's in my mind. So any particular point in space is a ratio of some thickness, it's a ratio of some length, it's a ratio of some color, it's a ratio of some light, it's ratio of it. So all
Yeah.
of these different ratios are the points that are the context. Yeah, okay, words fail.
So okay, allow me this. So if I have a canvas and I have a small object in the middle, and I color it, I give it a very specific color. If now I replicate it, the exact same thing to another canvas. Okay, so I have two canvas with the exact same shape in the middle, exact same color, and then without coloring on top of that shape, so I keep the original color. I change the color of the background.
Mhm.
So the initial shape and its coloration will appear differently if I apply a different coloration.
You bet it will. Yeah.
Yeah,
Yeah,
yeah.
you have two identical circles. Let's say they're both orange. And on one canvas, you paint the outer part, you paint it yellow. And on the other canvas, you paint the outer part blue.
Yeah.
The one that is the orange circle in the blue, that orange is going to be screaming off of that canvas.
Yeah.
And the one that's the orange surrounded by the yellow is going to look kind of dull and dark, right? And so it was Johannes Itten that did all this color theory work, and like back in the 1700s, maybe. And you can see all of his little diagrams and paintings of how these colors all relate to each other. So if you want to create luminosity in a painting so that the sunset is beautiful and just glowing in the midst of the scene, you're going to surround it with very soft, semi-neutral colors, like tending towards gray. Surround the sun with these soft grays, not a strong value contrast, but just an intensity contrast. That's the way you make it beautiful and luminous. So every color that you lay down, the context is based on what it's sitting next to. That principle is the same principle for every single one of these elements and principles, not just color, but it works the same way with value. If you put a small gray circle on two canvases and surround one of those gray circles with a lighter gray and surround the other circle with a darker gray, those two circles in the middle are going to look different. So yeah, it's all about context. But maybe we can talk about that when we get to your theory, your ideas about quantum information theory. Yeah, there you go.
Yeah, I just want to quickly share this painting. Basically, I find it the color on the trouser. I found it fascinating. This is a painting. I remember the painter now. It's a very old painter, but I really found it fascinating, and I wanted to share this with you. The colors and the way the painter is using the different aspects, especially in this part, I found it like amazing.
Yeah, well, you can see if you squint, the light areas are just the white around his hat and down the middle of his shirt and the guitar and the shoes, and everything else is pretty much a mid-tone dark. Okay. Now it gives the impression of being, even though there's not any bright colors in the painting, you get the impression that there is color there.
Yeah.
And you can clearly see whether colors are warm or cool because of the way he's put them next to each other. Yeah, it is a Manet. I thought so.
Yeah, the Spanish.
Yeah. So you can see the warm and cool, but you noticed, back up again, there's just a little bit of red in that painting, and you see how
Yeah.
the red just stands out?
Yeah.
There's three
Exactly.
places where the red stands out, and it stands out because everything else is a semi-neutral.
Yeah.
And then there's that little orange onion down at the bottom.
Yeah.
It's very fascinating because one of the things that I discovered about painting is that the viewer's eye tends to either fall out of the bottom of the frame or go towards the right to the next painting. So if you want to stop people in your painting, you put something down in the lower right-hand corner that keeps them from flowing away to the next painting on the wall. So he put a pot and 2 onions down.
Yeah.
That's terrific.
Yeah.
Hey, it's
Yeah.
time we got to wrap this up, but this has been great, Haris. I really love talking to you, and I look forward to hearing more about your ideas related to quantum information theory.
Awesome. By the way, Grim is gonna be very sad at me if I don't say this. Everybody, my name is like Haris, and so when he listens to some people calling me Haris, he keeps asking me like, "But why you never correct people when they mispronounce your name?" And I'm like, because it doesn't bother. I am not bothered by it. But yeah,
Okay, well, can you say it for me again?
yeah, it's Haris.
Haris.
Yeah,
That's not what I'm saying? No, I'm saying Haris.
Haris. You are saying
Yes,
Haris.
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 Okay.
Yeah.
I'm glad
So,
you corrected me.
yeah.
Yeah, I mean it's a very subtle distinction in my ear, but I'm sure to you it sounds strong.
Yeah.
Like sometimes with my name, people will call me Karen rather than
Yeah.
Karen.
Yeah.
And it's a very subtle distinction if you're used to Karen, but if you're used to Karen, it sounds,
Yeah.
startling. So
Awesome. So
when I lived in Japan, they used to call me Karen. You
Karen.
have to get used to it because they don't have the other pronunciation possible for them. So, but I can certainly learn to say Haris.
Thank you very much. Thank you for everything. I really enjoyed this, and yeah, looking forward to the next talk. And I will also share with you some of those clips from Julian Barbour. So,
Sounds great. We can put them in the description section under the video.
awesome.
Okay.
Awesome.
Have a great day.
You
Bye-bye.
too. Bye bye.